You may remember from Chapter 12 that aromatic carbons are one of the 4 classes of hydrocarbons, and even though the line structure can be drawn where there are 3 double bonds and 3 single bonds, that is not an accurate portrayal of the structure of benzene. So any compound that has a structure similar to that of benzene is known as aromatic, and we'll go over what that structure is. And that name aromatic is just historical, as a hydrocarbon with nonpolar bonds. The intermolecular force is going to be London dispersion force, which is very weak, and so many of these compounds have odors because the London dispersion force is weak, and there will be many of the molecules in the vapor phase. So anytime you smell something, it's because the molecules of that chemical are in the vapor phase. So here's experimental evidence number 1, that even though when we draw the line structure for C6H6, which is the chemical formula for benzene, and we draw 3 double bonds, when we look at the reactivity of benzene, it does not react like an alkene. We can add it to hydrogen, which in an alkene would form an alkane. We can add bromine to it, which in an alkene would form a 1,2-dibromoalkane. We can add HCl, which in an alkene would form a monochlorinated alkane. So we know that these reagents, hydrogen, halogen, HCl, HBr, react with alkenes. We know how to make that happen. When we add these to a benzene ring, no reaction happens. So that's experimental evidence piece number 1, that this does not react like an alkene does. Experimental evidence piece number 2 is the structure of benzene. So double bonds are shorter than single bonds, and when we were finally able to determine the structure of benzene, what we recognized, or what we realized, or what we saw, was that each carbon-carbon bond is the same length. So that means there are not 3 different types of bond, or 2 different types of bonds in this benzene ring. So the bond length is longer than a double bond and shorter than a single bond, and it's all the same length. So for our purposes, we can think of the skeleton, the carbon-carbon bonds, that is the same length. We can think of it as a single bond. A more correct term is sigma, but we'll just consider it to be a single bond. Now when we draw the Lewis dot structure from 6 carbons and 6 hydrogens, we have to draw these double bonds. So what do we do with these 6 electrons from these 3 double bonds if there aren't actual double bonds? Well, what we've realized is these 6 electrons that would be in these 3 double bonds in the line structure are not localized between 2 carbons. There's not a double bond between 1 and 6 where these 2 electrons are staying between 1 and 6. Rather, these 6 electrons from the 3 double bonds in the line structure, these 6 electrons are actually equally distributed among all 6 carbon atoms. And so this is why I prefer the line structure of benzene with the circle in the middle, because that helps us remember that those 6 electrons are actually equally distributed among all 6 carbon atoms, and that makes for a very, very stable molecule, which is why we didn't see any reaction, any addition reaction here. Now, we refer to this concept or this process as resonance, and you can recognize that resonance is going to happen anytime you can draw a double bond in more than one place on a molecule. So if we look at these 2 line structures with the double bonds for benzene, we see double bonds between 1 and 6, 2 and 3, 4 and 5. We also see double bonds between 1 and 2, 3 and 4, 6 and 5. Both of these are absolutely correct, but since every single carbon atom can be drawn with a double bond, then in the resonance, every single carbon atom is going to share those 6 electrons that would be in those 3 double bonds. So anytime you can draw a double bond in more than one place for a correct Lewis dot structure, you're going to have resonance, and those electrons that make up that double bond are going to be equally shared among all the atoms that would have that double bond in the Lewis dot structure. So that's how you can recognize when resonance occurs. We are mostly going to be focusing on benzene rings, but resonance can occur in compounds that aren't even hydrocarbons, just so you know. All right, so aromatic compounds, even though we draw the line structure with 3 double bonds, do not have double bonds. They have a special type of bonding due to the resonance